You know that feeling when you're trying to get your head around something huge, something complex, but it feels like you're just getting bombarded with jargon and bits and pieces.
Oh, absolutely. Information overload, it's everywhere. And it's especially true for, well, huge global challenges like climate change, right? And the sheer amount of CO2 we're dealing with.
Exactly. I mean, think about it. Something like 86% of the world's energy still comes from fossil fuels.
Yeah,
That's a staggering amount of CO2 heading into the atmosphere.
it really is. And it's why you see countries setting these ambitious targets. India, for example, aiming for a 45% cut in emissions intensity by 2030 and net zero by 2070. Big goals.
Huge goals. And we all know, that there isn't just one single magic bullet solution.
Mm-hmm. Which brings us to carbon capture, utilization, and storage. CCUS. It's this whole suite of technologies, really, that's becoming, well, pretty much essential for hitting those decarbonization targets.
So that's our mission today in this deep dive. We want to basically hand you the keys, unpack this whole CCUS puzzle, the science, the policy, the money, how it fits into society.
Yeah, we've dug through a lot of material, government handbooks, research papers, you name it, to try and distill it down.
Right. So by the end, you'll have the essential insights. You'll be properly informed on this really critical topic. Ready to jump in?
Let's do it. So first things first, why CCUS? And why now? The core problem, obviously, is the CO2 in the atmosphere. We're already way past 400 parts per million.
And most of that increase, it's us. It's human activity, burning coal, oil, natural gas.
And it's not just power plants either. Heavy industry is a massive piece of the puzzle. Petroleum refining, cement, iron, steel, aluminum. These sectors are really tough to decarbonize otherwise.
You really feel the urgency. I mean, you saw it at the big UN climate meetings, Paris in 2015, Glasgow in 2021. Everyone knows we have to cut emissions fast.
Exactly. And because the problem is so big, you need a whole portfolio of solutions. No single thing is going to fix it all. That's where CCUS slots in. It's vital.
And it's not just about the environment, is it? There's a strong economic case, too.
There really is. Trying to meet climate goals without CCUS, it could be way more expensive. Some studies say up to 138% more costly.
Wow. It's a massive difference. It makes it almost a financial necessity for some countries.
Yeah, it helps make decarbonization more affordable. And beyond that, think about the other economic ripples, job creation, innovation, trade opportunities. It can even help sustain existing industries while they transition.
And we're seeing a lot of focus on Asia, right?
Huge potential there.
Yeah.
Some projections suggest over half of all the CCUS projects by 2050 could be in the Asia-Pacific region. China and Japan are already making significant moves.
Okay, so let's get into the nuts and bolts. How does this CCUS thing actually work? You mentioned a value chain.
Yeah, think of it as 4 main steps, all linked together. Capture, then transportation, utilization, and finally storage, CCUS.
Got it. So starting with capture, where are we capturing this CO2 from?
Well, you've got what you might call the easier sources, high-concentration ones. Think ethanol plants, oil refineries, places making hydrogen or ammonia. The CO2 is already pretty concentrated there.
Okay, so less work to separate it out. But what about the big emitters, like power plants?
Right, that's the other category, low-concentration sources. This is the flue gas from power stations burning coal or gas, cement factories, steel mills, pulp, and paper. Here, the CO2 is mixed with a lot of other stuff, mostly nitrogen and water vapor, so it's trickier to grab.
Makes sense. So how do we grab? What are the main technologies? I hear a lot about amines.
Chemical solvents, yeah. And amines are the most common type. You can kind of imagine them like chemical sponges that soak up the CO2.
Sponges.
But the tricky part, the energy-intensive part, is squeezing that sponge to get the pure CO2 back out. That process, desorption, uses a fair bit of energy, often heat.
So that's why people say it's not always a totally green method itself, even though it's capturing CO2?
Exactly. There's an energy cost. Its theoretical maximum efficiency capturing CO2 versus the energy used is maybe around 50%. Still, it's a mature, widely used tech.
Okay, what else is in the capture toolkit?
Well, there's physical absorption. The Rectisol process is a classic example, developed way back in the 50s. It uses methanol, really cold methanol, like sub-zero temperatures.
Wow, chilling.
Yeah, it absorbs CO2, but also other things like hydrogen sulfide. You can remove things in steps.
Interesting. Any newer approaches?
Definitely. Ionic liquids are getting a lot of attention. These are basically salts that are liquid below 100 degrees Celsius.
Liquid salts.
Yeah. And the cool thing is they don't evaporate easily, and you can actually tune their structure, design them almost, to be better at grabbing CO2, potentially using less energy than the standard amines.
Okay, that sounds promising. What about getting even colder?
Ah, you're thinking cryogenic CO2 capture, or CCC. This is where we get really cold, like minus 100 Celsius.
Minus 100.
Yeah. The idea is to use that extreme cold to force the CO2 to change phase, turn it into a liquid, or even a solid like dry ice separating it from the other gases.
So you literally freeze it out.
Pretty much, you can condense it into a liquid.
Yeah.
Or some newer methods actually freeze it into a solid frost and then collect it. It gives you a very pure CO2 stream.
Fascinating. Are there non-temperature-based methods too?
Oh, yes. Membranes are another big area. Think of a super selective filter. You apply pressure, and the membrane lets CO2 pass through more easily than other gases, separating them out.
Like a bouncer for molecules?
Sort of. And then you have sorbents. These are solid materials that CO2 sticks to. Zeolites are a common type. They're minerals with tiny pores that trap CO2 molecules, kind of like a molecular sieve. They're pretty robust, too.
Okay. And I've heard about MOFs, metal organic frameworks.
Yes. MOFs are really exciting. They're like designer materials. You combine metal ions and organic linker molecules to build these incredibly porous 3D structures, like tiny cages, perfectly sized to trap CO2. They have amazing capacity for CO2 uptake, and you can tune the pore sizes. The big challenge right now, though, is making them cheaply and at a massive industrial scale.
Right, the classic scale-up problem. Any others we should quickly mention?
Sure. There are polymeric materials being developed and also chemical looping combustion, which is a different way of burning fuel that produces a concentrated CO2 stream directly.
It's amazing how many different angles scientists are attacking this from. Is this stuff actually working out in the real world?
Absolutely. Look at Alabama Power's Plant Berry. Back in 2009, they started a 25-megawatt pilot project using an advanced amine solvent. It was the world's largest on a coal plant at the time.
25 megawatts, that's pretty significant for a pilot.
It was. And they successfully captured, piped, and stored over 100,000 tons of CO2 deep underground. It proved the concept worked.
And that led to bigger things.
It did. That experience helped pave the way for the much larger Petronova project at NRG's WA Parish plant near Houston, a 240-megawatt capture system that ran for several years. It showed this can be done at a really substantial scale.
Okay, so we've captured the CO2. Step 2 was transportation, right?
Yeah.
How do we move this stuff?
Pipelines are the main workhorse, definitely the most common for large volumes over long distances. But depending on the situation, you might also use trains, ships, barges, or even trucks for smaller amounts or shorter hops.
Gotcha. Which brings us to the utilization.
Yeah.
What can we actually do with captured CO2?
Right. This is about finding uses for it, sometimes turning it into something valuable or storing it in products. A really established use is enhanced oil recovery, EOR.
You mentioned that earlier, injecting CO2 to get more oil out.
Exactly. It's been done since the 70s. The CO2 mixes with the oil left in the reservoir, makes it less viscous, easier to pump out. And importantly, these are generally closed-loop systems, so the CO2 mostly stays underground.
Okay. Any similar techniques?
Yeah, there's enhanced gas recovery, EGR. Same idea, but for natural gas fields or sometimes coal seams, pushing out more gas.
So using CO2 to extract more fossil fuels.
Yeah.
But what about using it in different ways? Turning it into things?
That's a really active area of research and development. You can convert CO2 into building materials, for example. Think about curing concrete with it or making aggregates. That locks the carbon up long term.
Like turning emissions into buildings?
Kind of, yeah. Or into other products like carbon black, which goes into tires, or carbon fibers, or even plastics. It can also be a feedstock for making fuels or chemicals.
And algae. I think I read something about that.
Right, microalgal CCU, using CO2 to feed algae, which can then be harvested for biofuels or other products. And another big one is BECCS bioenergy with carbon capture and storage. That's where you burn biomass for energy and capture the resulting CO2.
Okay. And what about just nature? Doesn't nature absorb CO2?
It absolutely does. Oceans, forests, mangroves, seagrass beds, they're huge natural carbon sinks. There's even research into how things like seaweed farming could help. Some red seaweeds, for instance, drastically cut methane from cattle when added to their feed.
Wow.
And managing ocean chemistry, potentially using minerals, could help buffer ocean acidification and maybe even boost shellfish growth by taking up CO2. So yeah, natural solutions are part of the picture too.
Okay, so capture, transport, utilization. That leaves the final S, storage. Where does the CO2 go permanently?
Primarily deep underground, we're talking thousands of feet down into specific types of geological formations.
Like what?
The main targets are deep saline reservoirs. These are vast layers of porous rock, like sandstone, that are filled with very salty water, brine, totally unsuitable for drinking or agriculture. Or depleted oil and gas reservoirs, the spaces that used to hold oil or gas.
So we're putting it back where fossil fuels came from, essentially.
In some cases, yes. And we know those formations can hold fluids and gases securely for millions of years. Other possibilities include unminable coal seams, even some types of volcanic rock or organic shales.
And this isn't brand new, right? You mentioned EOR experience.
Exactly. Dedicated CO2 storage projects have been operating since 1996, like the Sleipner project in Norway. But that built on decades, nearly 50 years now, of experience injecting CO2 for enhanced oil recovery. So the understanding of how CO2 behaves underground is pretty advanced.
Okay, so it's deep underground, but how does it stay there? What stops it from just leaking back out?
Great question. There are actually 4 main trapping mechanisms working together over different timescales that provide security.
4 layers of safety, kind of.
You could think of it like that. First, and most immediate, is structural or stratigraphic trapping. Imagine the porous rock layer where you inject the CO2 is capped by a layer of impermeable rock, like shale, a cap rock. The CO2 is buoyant and wants to rise, but it hits this cap rock ceiling and gets physically trapped underneath like gas in an unopened soda bottle.
Okay, like a lid. That makes sense. What's next?
Second is residual trapping. As the plume of injected CO2 moves through the tiny pore spaces in the rock, some droplets or bubbles get left behind, stuck in the pores by capillary forces. Think of how a sponge holds onto some water even after you squeeze it. This traps a significant amount of CO2 relatively quickly.
Ah, okay, so it gets physically stuck in the rock's pores.
Precisely. The third mechanism takes longer. Dissolution or solubility trapping. Over time, the CO2 slowly dissolves into the salty water, the brine, that's already in the rock formation.
It just dissolves, like sugar in water.
Exactly. And when CO2 dissolves in brine, it actually makes the brine slightly denser. So the CO2-rich brine tends to sink slowly downwards within the reservoir, adding another layer of security.
Okay, sinking deeper. And the fourth one.
This is the ultimate long-term lock, mineral trapping. The dissolved CO2, which forms carbonic acid in the water, can chemically react with the minerals in the surrounding rock.
Reacts with the rock itself.
Yeah. It forms new, solid carbonate minerals. Essentially, it turns the CO2 back into rock. This is the most permanent form of storage, but it's also generally the slowest process it can take, anywhere from, well, minutes in some reactive rocks to potentially thousands of years to become significant.
Wow. Turning CO2 back into rock, that's pretty secure.
That's the goal. Multiple mechanisms working over different timescales, all contributing to keeping the CO2 safely locked away.
The planning for one of these storage projects must be immense. It sounds like a decades-long undertaking.
Oh, it absolutely is. The life cycle is incredibly long and detailed. You start with resource assessment, just finding and evaluating potential areas. That alone can take, say, 2 to 6 years.
Years just to assess.
Yep. Then comes design and development, maybe 1 to 5 years. Then construction, perhaps 1 to 3 years. The operation phase, the actual injection, can last for 20, 30, even 50 years or more.
50 years of injection.
Then you have closure, sealing the wells, which is variable. And finally, a long post-closure monitoring period, easily 10 years, often much longer, to make sure everything is stable.
It's a huge commitment. And you mentioned assessing multiple sites.
Crucial. You don't just pick one spot and hope for the best. You start broad and narrow it down, because the deeper you investigate a specific site, the more expensive it gets. You need to manage that exploration risk.
How does that narrowing down process work?
It's a funnel, really. You start with regional screening, looking maybe hundreds of potential storage formations using existing geological data, seismic surveys, old well logs. Very preliminary.
Casting a wide net.
Then site screening. You narrow it down to maybe 30 to 50 promising leads, doing more focused sub-regional analysis. Then site selection, where you pick a smaller portfolio, maybe around 20 sites, and start drawing up initial development plans.
Getting more serious now.
Exactly. And finally, initial and detailed characterization. This is where you really invest. You acquire new high-resolution data, maybe new seismic surveys, drilling appraisal wells, running tests to understand the rock properties, the cap rock integrity, and establishing baseline environmental conditions before any injection starts.
That sounds incredibly thorough.
Yeah.
You mentioned something about a book value for storage.
Ah, yes. The Storage Resource Management System, or SRMS. This is a standardized way to classify CO2 storage resources, kind of like the system the oil and gas industry uses for reserves, the PRMS.
So it gives it a formal status.
Precisely.
Picture.
It allows companies and governments to quantify the storage potential of a site in a consistent way, moving it from just a possibility to something more like a recognized resource, or eventually a bankable capacity. It helps unlock financing because investors can see a more tangible asset.
That makes a huge difference, I imagine. Okay, so the CO2 is down there. We think it's trapped. But how do we know? How do we monitor it?
Right. That's where measurement, monitoring, and verification MMV comes in. It's absolutely essential, and usually it's legally required.
Measure what you manage, basically.
Exactly. Peter Drucker's wisdom applies perfectly here. MMV is about confirming the CO2 is behaving as predicted, that it's staying put, detecting any potential issues early, and ultimately ensuring long-term safety and building public confidence.
So what exactly are we measuring and monitoring?
It starts before injection with baseline data. You need to know the starting conditions. The quality of seabed sediments if it's offshore, the natural pressure and temperature in the reservoir, what fluids are already down there, the condition of any existing wells.
Establishing the before picture.
Precisely. Then, during injection and after closure, the monitoring is ongoing. You're tracking where the CO2 plume is moving underground. Time-lapse seismic surveys are key here, shooting seismic waves down periodically and comparing the images to see how the CO2 is spreading.
Like underground weather radar for CO2.
Kind of. You also monitor reservoir pressure and temperature very closely. You listen for any tiny earthquakes. Microseismic events, though, as we said, significant induced seismicity is generally very unlikely, usually below magnitude 2.
Okay, what else?
You monitor the wells themselves, both the injector and any old legacy wells nearby, checking their integrity. You look at the rock layers above the storage zone, the overburden to ensure nothing's getting through. You check for any ground surface movement, like tiny amounts of uplift or subsidence. And of course, you monitor the surrounding environment, the marine environment, if offshore, groundwater, air quality near the site.
What kind of tools do you use for all this?
A whole range of sophisticated technologies. Fiber optic cables can be installed in wells to continuously measure temperature, DTS, or acoustic signals, DCSS, which can track the CO2 movement or listen for leaks. Ultrasonic tools check the condition of the well casing and the cement behind it. For offshore, remotely operated underwater vehicles, RUVs, might be used to survey the seabed or sample water.
You mentioned legacy wells. That seems like a potential weak point, right? Old wells that weren't designed for CO2.
It's definitely a key risk that needs careful assessment. Wellbore integrity, especially for old, plugged, and abandoned P&A wells, is critical. Over very long time scales, hundreds, thousands of years, the cement plugs or metal casings could potentially degrade from interaction with CO2-rich fluids.
So you need to know where they are and make sure they're properly sealed for the long haul.
Exactly. Thorough assessment and potential remediation of legacy wells is a big part of site evaluation and risk management.
And all this MMV data, it's not just for the engineers, is it?
Absolutely not. Communicating the results clearly and transparently is vital for public trust. Showing people the monitoring data, explaining what it means, demonstrating that the storage is working safely, that's crucial. This can involve monitoring CO2 levels in the air and soil around the site, maybe using chemical tracers added to the injected CO2 to distinguish it from natural sources, and having advanced leak detection systems on pipelines.
Building that confidence is key, which leads us nicely into managing the broader risks. What could potentially go wrong, and how are projects designed to prevent that?
Right. Risks generally fall into socioeconomic, like public acceptance, market issues, and technical categories. Let's focus on the main technical ones. There are about 5 key areas.
Okay, lay them out for us.
First, site performance risks. Basically, the reservoir not behaving exactly as predicted. The Snøhvit project in Norway is a good case study.
What happened there?
They started injecting CO2 offshore in 2008, but the pressure in the injection formation built up faster than expected. They had to adapt. They stopped injecting into that initial zone and started injecting into a different, deeper formation. Eventually, they even drilled a second injection well. It shows you need flexibility and good monitoring to manage subsurface surprises.
Okay, so performance can deviate. What's next?
Health, safety, and environmental risks, or HSE. This is the potential impact if CO2 did leak. CO2 itself isn't toxic in the way some industrial chemicals are, but in high concentrations it displaces oxygen and can cause asphyxiation. A large, rapid release could also harm local ecosystems.
How likely is that?
With proper site selection, operation, and monitoring, major catastrophic leaks are considered extremely unlikely. Studies, like one from the UK, acknowledge CO2 is hazardous in concentration, but find the likelihood of major incidents is very low if the right controls are in place.
Okay. Third risk category.
Containment risks. This is specifically about pathways for CO2 or displaced brine to escape the storage formation. It could potentially migrate upwards through natural faults or fractures in the caprock. The probability of that is generally considered low to medium, depending on the site geology.
And the wells again?
Yes, wells are another potential pathway. For wells built specifically for CCUS and monitored properly, the risk is negligible to low. But, as we discussed, those unknown or improperly sealed legacy wells pose a higher, though still generally low, probability risk if not addressed.
Got it. What about earthquakes? Does injecting CO2 cause them?
That's the fourth risk: induced seismicity. Injecting fluids can slightly increase pressure in the subsurface, which could potentially trigger tiny earthquakes, usually too small to feel. The risk of triggering larger, damaging earthquakes from CO2 injection is considered very low, especially compared to, say, wastewater disposal in some areas.
Any real-world examples?
The Tomakomai project in Japan is interesting. A natural magnitude 6.6 earthquake happened about 30 kilometers away from the offshore storage site. Extensive monitoring after the quake showed no signs of CO2 leakage, indicating the storage remains secure even after significant nearby seismic activity.
That's reassuring. Okay, final technical risk.
Resource interaction risks. This is about the stored CO2 potentially migrating into and contaminating other valuable subsurface resources, like shallower freshwater aquifers, or maybe interacting negatively with remaining oil and gas deposits or coal seams.
How big a risk is that?
In a well-selected and managed site, the risk is low. The storage zones are typically much deeper than drinking water sources and separated by multiple layers of rock. But if a site was poorly chosen or containment failed significantly, contamination is a potential consequence. That's why site selection and MMV are so critical.
So how do projects manage all these risks? What are the key strategies?
It boils down to a few core things. First, incredibly detailed site assessment and characterization, knowing the geology inside out. Second, careful pressure management during injection, for example. Regulations like Alberta's limit injection pressure to well below the rock's fracture pressure. Third, robust, long-term MMV programs. And fourth, thorough assessment and management of any legacy wells.
Makes sense. It's a complex technical challenge, but it sounds like the risks are understood and manageable with the right approach.
That's the consensus, yes. But doing it right requires more than just good engineering. You need the whole ecosystem around it.
Ah, right. Policy, finance, people, the whole infrastructure. Let's talk about the legal and regulatory side first. That sounds crucial.
Absolutely essential. You need a clear framework. Policies, laws, acts, regulations, all the legal stuff that provides structure. It needs to offer predictability for investors, clear rules for operators, accountability, transparency, and ultimately make these projects bankable.
How does a country even start building that framework?
There's often a roadmap approach. Step one is usually looking at what policies and laws already exist that might apply or need adapting. You see this in places like Malaysia looking at their energy transition plans, or India with reports from the NIAOG.
So you build on what's there.
Often, yes. Norway, for instance, adapted its existing Petroleum Act to cover CO2 storage. Other places might decide to create entirely new, specific laws just for CCUS.
Are there international guidelines helping with this?
Yes, definitely. Standards like ISO 27914 provide technical guidelines for geological storage. And international agreements matter too. The London Protocol, for example, was amended to allow CO2 to be transported across borders for offshore storage.
Cross-border CO2.
Yeah. Project Greensand is a great example, capturing CO2 in Belgium, shipping it to Denmark, and storing it under the North Sea. The Espoo Convention also plays a role, requiring environmental impact assessments if a project in one country might affect another.
Okay. And within a country's framework, what are the key things a project needs clarity on?
Several big ones. Who owns the CO2? Who is liable for the storage site long term? Often, responsibility transfers to the state after a defined post-closure monitoring period, like in Alberta. Clear environmental assessment processes are vital. Community engagement needs to be built in. How do you match sources with storage sites? The idea of hugs and clusters is important here. And of course, the financial side, taxes and incentives.
Right, the money. These projects sound expensive.
They are. Capital costs are significant. A capture plant alone could be anywhere from $50 million to over $1 billion, depending on the scale and technology, plus ongoing operating costs.
So how do they get financed?
Proximity helps. Having a good storage site near the capture facility cuts down transport costs. But government action is usually critical to bridge the economic gap.
What can governments do?
They have a few levers. They can use mandates, things like a carbon tax, or direct regulations like the proposed U.S. standards for power plants. Or they can offer incentives, funding for research and development, grants for projects, direct investment, tax credits, loan programs.
Tax credits seem to be a big driver lately.
Huge. The U.S. Section 45Q tax credit, especially after being boosted by the Inflation Reduction Act, has been a game changer. It provides a significant per-ton credit for stored CO2. $85 for geologic storage, $60 if used for EOR, and even more, $180 or $130 for direct air capture. That really shifts the economics.
And Canada has something similar.
Yes, Canada introduced a substantial CCUS investment tax credit, 50% for capture equipment costs, 37.5% for transport and storage. These kinds of direct financial incentives are powerful.
What about market-based approaches, carbon taxes or trading systems?
Those play a role too. Carbon taxes provide a clear price signal, but there's the risk of carbon leakage companies just moving production elsewhere. Cap-and-trade systems, like the EU's emissions trading system, ETS, create a market for emission allowances. If you emit less or capture your CO2, you need fewer allowances, which saves money or lets you sell spare ones.
So CCUS becomes a way to comply or profit within the system.
Exactly. Some places, like Norway, actually stack incentives. They have a high CO2 tax on top of being part of the EU ETS.
Any downsides to these financial mechanisms? Unintended consequences.
Well, sometimes poorly designed incentives can have odd effects. Capping the total amount of credits available might limit investment, for instance. Or sometimes focusing only on CCUS credits might discourage companies from making other, perhaps cheaper, emission reduction investments first. It's a balancing act.
And there are external pressures pushing this, too.
Definitely. Things like the EU's Carbon Border Adjustment Mechanism, CBAM, basically a carbon tariff on imports, are putting pressure on industries globally to track and reduce their emissions. There's also growing demand from investors and regulators for transparent emissions reporting, driven by groups like the International Sustainability Standards Board. And the growth of carbon markets, both compliance and voluntary, creates more potential revenue streams for captured CO2, although integrity issues like double counting need careful management.
Okay, so you've got the tech, the policy, the finance.
Yeah.
But who actually does all this work? You need skilled people.
Absolutely critical. Capacity building. You need a huge range of skills. Chemical engineers, mechanical engineers, process engineers for the capture plants, geologists, geophysicists, reservoir engineers for the storage side, chemists, drillers, pipeline operators, monitoring specialists. The list goes on.
Sounds like a lot of jobs, potentially.
It is. It's a real opportunity for creating sustainable long-term employment in the energy transition.
How do you build that workforce and expertise?
Several ways. Embedding training and local hiring into project development and outreach is important. Building strong professional networks helps share knowledge. And establishing dedicated testing and training centers is proving really effective.
Test centers, like where they try out new technologies.
Exactly. The National Carbon Capture Center, NCCC, in the U.S. is a prime example. It's a neutral test facility hosted by Southern Company. They've tested over 75 different capture technologies there, helping to bring down costs. They reckon they've contributed to a 40% cost reduction for capture from power plants.
Wow, 40%.
Yeah. And they don't just test capture, they test carbon conversion too, turning CO2 into ethylene or low-carbon concrete, feeding algae, testing direct air capture technologies. It's a real hub of innovation.
Maybe others like that.
Norway's CO2 Technology Center Mongstad, TCM, is another world-leading facility. It's co-owned by the Norwegian state and major energy companies like Equinor, Shell, and Total Energies. They've run over 20 major test campaigns for different solvent and emerging technologies.
And that helps real projects.
Immensely. The testing and learning at TCM were absolutely critical for developing Norway's big, long-ship CCS project. And TCM actively shares its knowledge globally. It's part of an international test center network.
Beyond big test centers, what about training individuals?
There are specialized programs. The IEEGHG runs an international interdisciplinary CCS summer school, brings together young researchers and professionals from around the world. In the U.S., the Research Experience in Carbon Sequestration, our ECS program, offers an intensive 8-day immersion for grad students and early career folks, including site visits and networking. It's a model other countries could copy.
And specific national efforts.
Sure. India, for example, established a National Center of Excellence in CCU at IIT Bombay. They're focused on developing novel, low-cost capture methods suited to Indian industry and advising the government on CCUS policy.
It really takes a village, doesn't it?
Yeah.
Tech, policy, money, people, and community support. Let's talk about the human element, public engagement. How important is that?
Paramount. Absolutely crucial. Lack of public understanding or acceptance has delayed or even canceled CCUS projects in the past. You simply cannot succeed without engaging the public, especially local communities, early and effectively. Policymakers and regulators need to lead on this too.
What does good engagement look like? What are the key principles?
It starts with genuinely understanding the community's values, concerns, and questions. You need to engage early, before major decisions are made, and keep engaging throughout the project life. Involve the community in decision-making where possible.
So it's not just telling them what's happening.
No, it has to be a two-way exchange. Establish clear guidelines for respectful dialogue. Facilitate genuine back and forth. Build collaboration. Always connect the specific project back to the bigger picture. Why is CCUS needed? Why here?
What else?
Be flexible. Make sure information is accessible. Use clear language. Avoid jargon. Provide translations if needed. Visuals help a lot. Graphics, maps showing depth scale so people understand how deep the storage is. And link it to local benefits like workforce development, training, internships.
Any examples of this being done well?
The Houston CCS Alliance is a good case study. It's a group of major industrial emitters in the Houston area working together on potential large-scale CCUS hubs. They've put a lot of effort into community education, holding public discussions, creating bilingual resources, sponsoring local events, engaging volunteers. It's about building awareness and hopefully positive perception over time.
What are the biggest hurdles with public perception?
Often it's just low awareness. Many people haven't heard of CCUS or don't understand what it is. There's also sometimes conflation with the oil and gas industry, a perception that it's just about enabling continued fossil fuel use, rather than managing unavoidable emissions.
So reframing is needed.
Exactly. One useful approach is framing CO2 management as fundamentally waste management. People understand the need to safely manage municipal waste or industrial byproducts. Thinking of CO2 in the same way as an industrial waste product that needs responsible, permanent disposal can sometimes resonate better. It's about taking responsibility for emissions.
That's a powerful analogy. Okay, we've covered a ton of ground. Technology, policy, finance, people. Now, you hinted earlier about data and AI. This sounds like where things get really cutting edge.
Yeah, this is where CCUS is starting to intersect with these powerful exponential technologies. Think about how other industries have been totally transformed by data. The music industry is a classic example.
From vinyl and tapes to streaming everything.
Exactly. Data became democratized, reusable. A single song recording became the source for countless events, streaming plays, playlist additions, recommendations. This drove prediction, customization, totally new value creation.
So how does that apply to CCUS? How can AI and machine learning help?
In so many ways. These tools enable disruptive solutions across the whole chain. Think predictive maintenance for capture plant equipment, reducing costly downtime.
Okay, that makes sense.
Or using AI to accelerate the discovery of novel materials, finding those next-generation solvents or MOFs much faster than traditional trial and error.
Speeding up innovation. Cool.
Absolutely. And for safety, AI algorithms analyzing sensor data from pipelines to provide real-time, highly sensitive leak detection.
Critical for transport. What about the storage side? That seems data heavy.
Hugely. AI and ML are revolutionizing site characterization. You can feed algorithms vast amounts of geological data, seismic surveys, logs, core samples, and they can help identify the most promising storage locations much more efficiently. They can even help predict things like a relative carbon storage index for different areas.
So finding the best spots faster.
And with more confidence. It involves amalgamating diverse data types, filtering that data intelligently, using specific seismic attributes like RMS frequency or sweetness that tell geoscientists about rock properties, or log data like density and gamma ray, and then applying sophisticated models.
What kind of models?
Things like aggregated tree models, often called random forests, which are great for prediction. Using techniques like stratified cross-validation to ensure the model is robust. Measuring performance with metrics like R2 score or root mean squared error. It's bringing rigorous data science to subsurface interpretation.
It sounds like it's augmenting human expertise, not replacing it.
Precisely. Augmenting physics-based understanding with data-driven insights for faster, better decisions. Same applies to optimizing drilling performance for injection wells.
Can you quickly clarify AI versus ML? People use them interchangeably.
Good point. AI, artificial intelligence, is the broad field making machines smart. Machine learning, ML, is a subset of AI where systems learn from data without being explicitly programmed for every task.
And there are different types of ML.
Yep. Supervised learning is common. You train the model with labeled data, like classifying rock types as good seal or poor seal. Unsupervised learning finds patterns in unlabeled data, maybe clustering areas with similar geological properties. And semi-supervised uses a bit of both.
What are some specific ML techniques being used?
Support vector machines, SVMs, are good for classification tasks. Random forests, as mentioned, are powerful ensemble methods for prediction. And deep learning, which uses artificial neural networks with many layers, things like CNNs, RNNs, GNs, LSTMs, is proving incredibly effective, especially with complex, sometimes sparse subsurface data for finding hidden patterns in relationships.
So what's the bottom line value here? What does AI bring to CCUS?
It fundamentally enhances our ability to predict, assess, detect, optimize, and automate. It helps us better predict critical factors like how well the caprock will seal, or estimate the storage capacity with greater accuracy. It's driving the CCUS industry towards what you might call digital maturity, being truly data-driven and AI-enabled.
Wow, that adds a whole new dimension to everything we've discussed.
It really does. It's accelerating progress and improving efficiency across the board.
Okay, let's try and wrap this up. We have covered an incredible amount of ground today. From the fundamental science of capturing CO2, transporting it, finding uses for it, and storing it securely deep underground.
To the vital importance of measuring and monitoring, understanding, and managing the risks involved.
Through the complex ecosystem of policy frameworks, financial incentives, and the absolute necessity of building human capacity and engaging the public.
And finally, touching on how data science and AI are poised to really turbocharge the whole field.
It's clear CCUS isn't just one thing, it's a whole system, a critical piece of the puzzle for tackling climate change. And it's evolving rapidly.
It really is. The technology is advancing, the policies are developing, the financial tools are getting sharper, and now these digital technologies are adding a whole new layer of capability.
So maybe a final thought to leave our listeners with. You mentioned earlier that the reservoir is always right. The geology does what it does.
Right. Our models are just approximations of that complex reality.
So, if the reservoir is always right, how might our rapidly improving ability to understand that reservoir, using all this data, all this AI, combined with our growing experience, how might that fundamentally change not just how we manage carbon storage, but maybe even how we think about our long-term relationship with the planet's subsurface, our stewardship, if you like?
That's a deep question. It shifts the perspective from just disposing of CO2 to perhaps more actively, intelligently managing subsurface resources and processes on a planetary scale. It's definitely something to ponder.
Indeed. Plenty to think about there as you consider all this information and what it means for our energy future and the technologies shaping it.